Okay, so it is time to continue. I hope everybody can hear me. We have in the last class started to look at translational symmetry in crystalline solids. And we discussed also how in this context we can describe extended solid with translational symmetry, also called a crystalline solid. And I had mentioned that we can describe such a solid by what is called the crystal structure. And the crystal structure, as we discussed also, is composed of the lattice as well as the basis, also called the motive. So the lattice is a mathematical construction. It's just an infinite array of points in space in which each point has identical surroundings to all the others. So according to this definition, there is inherently translational symmetry within a lattice. That again means that you can define translational vectors that move all the lattice points so that they superimpose and they become indistinguishable from their original form. So within that lattice, there is the basis of the motive. So the basis of the motive is nothing else but the atoms within the lattice. So the atoms can either sit on the lattice points, but not necessarily they have to. They can also sit in between the lattice points, but they also have to follow translational symmetry, and they have to follow, therefore, the symmetry of the lattice. Now, the last point we discussed was that in an extended solid, as the name says, we have, well, in principle, an infinitely large structure. So the question is, how can we describe the crystalline extended solid in the most concise form? And that led us to the concept of the primitive cell and the unit cell. So just to review this also, the primitive cell is the simplest cell with the smallest volume containing only one lattice point. Okay, while the unit cell is the smallest cell of the crystal, which shows the full symmetry of the lattice. So both the primitive cell and the unit cell are repeating units. Okay, they are repeating units within the lattice, and to describe the entire lattice and describe the entire crystal structure, we only need to basically add the unit cell next to each other in all three dimensions when we have a three-dimensional crystal structure, and these additions then produce the entire crystal structure. So let us look more closely at unit cells and lattices. So again, the forward button does not function. So at least, or it functions very smallly with a very large delay, not clear exactly why. So in order to understand unit cells, we need to look at their symmetry in more detail and how we can classify them according to their symmetry. So each unit cell belongs to crystal systems. So for simplification reasons, we first look at two-dimensional unit cells with two-dimensional crystal systems. And in the next step, then we will go to three-dimensional unit cells with three-dimensional crystal systems. So in 2 dimensions, there are overall 4 crystal systems that have particular unit cells associated with them. So the crystal system with the highest symmetry is the so-called square crystal system. So in the square crystal system, we have lattice points that contain a unit cell in which the unit cell parameters A and B are the same, and in which the angle between the unit cell parameters A and B are equal to 90 degrees. So you see this square crystal system here, and you see the unit cell associated with the square crystal system in it. And you see that the unit cell just resembles a square, and a square necessarily both edges have the same length. So these edges, they represent the unit cell parameters A and B, and the angle in between these two unit cell parameters, they have an angle of 90 degrees. We can easily see that this unit cell represents a repeating unit for the entire lattice. So in this case, our unit cell is a so-called primitive unit cell because it is not centered. That means that there are no additional lattice points within the unit cell. So now we can go to lower crystal symmetries, the lower lattice symmetries. We can, for instance, make the unit cell parameters A and B unequal, but still keep the angle in between A and B equal to 90 degrees. Then we go to what is called the rectangular crystal system. So you see that in the rectangular crystal system, we have a rectangular unit cell, but now the lattice parameters A and B are unequal, but still the angle in between A and B is 90 degrees. Again, this is a primitive unit cell because lattice points exist only on the corners of the unit cell, but there's no additional lattice point within the unit cell. There's no additional lattice point in the center of the unit cell. Okay, so now we can lower sorry, the symmetry of our lattice further. We can go to a lattice in which now these rows here of lattice points are offset relative to each other. Okay, in contrast to here, the rows of lattice points are offset relative to each other, and therefore the symmetry is being lowered. So now when you look for the primitive cell, which represents the cell with the smallest volume, then you will find that it is defined by these 4 lattice points here. Okay, so now is this the unit cell? The answer is no, this is not the unit cell because it does not reflect the full symmetry of the lattice. It actually overlooks that we can define a somewhat larger cell which has a higher symmetry and which is now centered. Okay, so now again we have we are therefore staying within the rectangular crystal system, but now we have a centered rectangular unit cell. And we have a centered rectangular lattice associated with it. Okay, so again we have A is unequal to B, and gamma is still 90 degrees. The angle is still 90 degrees, but now there's a lattice point in the center of this rectangle. Okay, so we have a centered rectangular lattice. Okay, so this is now not primitive anymore. We say it is centered because we have an additional lattice point in the center. All right, so then there are two more possibilities actually. We have also a hexagonal crystal system. And in that hexagonal crystal system, we have a unit cell in which, again, A is equal to B, but now the angle in between A and B is 120 degrees. And that creates a six-fold axis, which actually sits on each lattice point. So if you rotate the lattice around that six-fold axis, all lattice points will superimpose with the original lattice and is indistinguishable, proving that that symmetry operation is present. So Tom raised the hand. Tom, can you unmute and ask your question?
Yeah, it's just a quick question. The difference between the centered rectangular and the hexagonal, why, if the hexagonal has the six axis rotation for the symmetry, why would you not use that same construction for the centered rectangle, you know, make that diamond looking hexagonal lattice, because it looks very, very similar, just a little more spread out.
Yeah, you're raising a very good point. So you could also define a rectangular unit cell which is centered. So for instance, if you connected these 2 points and these two, yeah, you could also form a rectangle which is centered. Okay, but that unit cell would not reflect the hexagonal symmetry. Okay.
Right. So my question is opposite. Why wouldn't you do that for the? Why wouldn't you make the centered rectangular hexagonal?
Because it's not. There's no hexagonal symmetry. Okay, and there's not a hexagonal symmetry because A and B are not unequal. Are unequal. So unless A is equal to B, this six-fold axis is eliminated.
Okay.
Okay. So this is not a regular hexagon by which each lattice point is surrounded. Yeah. I mean, there's still 1, 2, 3, 4, 5, 6 lattice points surrounding a central lattice point, but not exactly in a hexagonal fashion. Therefore, no six-fold axis is there. Whereas here, really a six-fold axis is there.
Now I understand. Okay, so it's A, gotcha. Thank you.
All right. So now how do we define the unit cell in the hexagonal crystal system? So one would actually see the hexagonal symmetry more clearly if we defined the unit cell as a hexagon, like this one, yeah, which is centered. However, the six-fold symmetry can only be seen when you define a smaller unit cell, such as this primitive unit cell. Okay, because if you put yourself on a particular lattice point and consider that the six-fold axis actually is on that lattice point standing perpendicular to this plane here, then it will actually move the lattice point correctly from one position into the next. So this lattice point will move here if you carry out the six-fold rotational axis. this lattice point will move here when you carry out the 6-fold rotational axis. Therefore, we define this primitive cell here as the unit cell of the hexagonal crystal system. So this is the third possibility for a crystal system, and the fourth possibility to define a lattice. Now the fourth possibility to define a crystal system is shown here. So this crystal system here has lattice points that are defined by a so-called oblique unit cell. And then in this oblique unit cell, the lattice parameters A and B are unequal, and the angle in between the lattice parameters A and B are unequal to 90 degrees. Okay, so you see this here. So the distance between this lattice point and that lattice point is unequal to the distance between this lattice point and that lattice point. So we can therefore define this as the lattice parameter A, and this here is the lattice parameter B. So the angle in between here will be unequal to 90 degrees. It's, by the way, yeah, it can actually be 120 degrees, and it's still not hexagonal because A is unequal to B. All right, so this crystal system is called the oblique crystal system. So now that is all which is possible in 2 dimensions. So we can have overall 4 crystal systems associated with 5 different lattice types, and these are called the 4 Bravais lattices that there can be in 2 dimensions. Okay, now we can go from 2 dimensions to 3 dimensions, and according to the same considerations, we can derive crystal systems and Bravais lattices. Now let us look at the crystal systems first. So now in 3 dimensions, we can have 7 instead of 3, sorry, 4 crystal systems. So the crystal system with the highest symmetry is the cubic crystal system. So in 3 dimensions, we have 3 lattice parameters, A, B, and C. And for a cubic crystal system, A is equal to B, which is equal to C. And the angle in between A, B, and C is equal to 90 degrees. So that defines a cube as the unit cell of our cubic crystal system. So when we lower the symmetry and make B unequal to C, but still leave A equal to B and the angle in between the 2 lattice parameters to be 90 degrees, then we have the so-called tetragonal crystal system. Okay, and you see the associated unit cell here, so we do not have a cube anymore, but a cube which is either elongated or compressed in one particular direction. So now we can further lower the symmetry by making now B unequal to A and C unequal to B, and also, by the way, C unequal to A, but still leave the angle 90 degrees, and then we have we are in the so-called orthorhombic crystal system, having an orthorhombic unit cell. So we can further lower the symmetry. So when B is unequal to A and C unequal to B, and we eliminate the 90-degree angle, then we go to the monoclinic crystal systems. So in the monoclinic crystal system, only one 90-degree angle is eliminated. So there's still one 90-degree angle there. Okay, so you see actually you have here still a 90-degree angle. Okay, within these two rectangular faces, but the second angle, the angle beta, is now unequal to 90 degrees. So if we go symmetry-wise even lower and make A unequal to B unequal to C and alpha unequal to beta unequal to gamma unequal to 90 degrees, then we are on this so-called triclinic crystal system, and you see the associated unit cell over here. So then there are two more crystal systems to consider. There's the so-called hexagonal one that contains a six-fold axis. And in the hexagonal one, we have A equal to B being unequal to C, and alpha is equal to beta is equal to 90 degrees, and gamma is 120 degrees. Okay, and you see here the unit cell which is associated with it. Okay, so you see in this case that the 90-degree angle is actually here, and there's a 120-degree angle which is actually here. Okay, again, the primitive cell is defined as the unit cell, not the centered larger cell, which would actually contain an entire hexagon. Yeah? So this is actually not the unit cell here, only the small primitive unit cell is defined as the hexagonal unit cell. So the last case is the rhombohedral crystal system with the rhombohedral unit cell. And in this case, we have A equal to B equal to C, and alpha is equal to beta and equal to gamma, but they are not 90 degrees, because if they were, we would have a cubic case. From that, you can see that you should be able to derive the rhombohedral unit cell from a cubic unit cell. And I would like to show you briefly how. And in order to do that, I will briefly stop the screen sharing. So now you should see me again on the large screen. Is that correct? I hope so.
Yes.
Okay. And you see here now, I have a cube in my hands. I can hold that into the camera. So you see this is a cube. Yeah. So this shall be our cubic unit cell. So how can we derive the rhombohedral unit cell from the cubic unit cell? And we can do this by actually distorting that cube by pulling at two opposite corners along the space diagonal. Okay. So now if I just hold my object like this, you see that because of gravity, my cube tends to distort. So of course the edge lengths are still all the same. A is equal to B, which is equal to C, but now the angles are not 90 degrees anymore. The angles are actually also all equal, but they're not 90 degrees anymore. Okay. So why is this rhombohedral unit cell special in symmetry? That is because it contains a trigonal axis, and that trigonal axis actually goes, or threefold axis goes actually through these opposite opposite corners here. Okay, so you can rotate this by 120 degrees, and then the unit cell superimposes. Okay, so this is different from hexagonal, obviously, where we have to have a 6-fold axis. Here we do not have a 6-fold axis, but only a 3-fold axis. It's also different from cubic in the sense that we do not have a 4-fold axis. In the cubic case, of course, we have a 3-fold axis also, but in addition to that, we have a 4-fold axis, of course, which goes to the middle of the squares. Yeah, so here, the 4-fold axis would actually go through the middle of the square. All right, so we can now go back to screen sharing. And we have now discussed all the 7 different crystal systems. And in the next step, we can now look at what lattices are associated with these 7 different crystal systems. So at least there should be 7, but there may be more, because we may be able to center the unit cells in specific ways, creating additional lattice types. So let us go through the crystal systems step by step and see what possibilities we have to center the unit cells. Okay, let's go to the cubic system first. So the first possibility is to face center the cubic unit cell. So that means that we have additional lattice points on the, well, face centers of the cube. So you know that a cube has overall 6 faces. So we have overall 6 face centers on the 6 faces of the cube. Okay. So many metals crystallize actually in this crystal structure. We call this the lattice type F for face-centered. For instance, silver, gold, aluminum, nickel, and many other metals have unit cells which are cubic face-centered. So you have, hello? Was that a question? No, doesn't seem so. Okay, so in these crystal structures, we have atoms on the corners of the unit cell. In addition to that, we have the same type of atom on the face centers of the unit cell. All right, so the second possibility is to have a body-centered cubic unit cell associated with a body-centered cubic lattice. We also call this the lattice type I. So in this case, you have an additional lattice point in the center of the cubic unit cell. So again, a number of metals crystallize in that lattice type. For instance, alpha iron makes a body-centered cubic structure. We have iron atoms on the corners of that cubic unit cell, and then we have additional iron atom in the center of that unit cell. This is just one example. There are many others like niobium, tantalum, barium, molybdenum, and so forth. All right, what else is possible? Well, then there's of course the primitive case possible. Okay, it is important to understand though that primitive does not necessarily mean that there's no atom in the center of that primitive cubic cell. Okay, so for instance, in cesium chloride, we have a primitive cubic cell. So we have chloride ions on the corners of that unit cell, and the cesium is in addition, is in the center. So at first glance, you may think, well, that is a body-centered cell, but it's not, because the criterion is that there has to be an additional lattice point in the center of that unit cell. And translational symmetry must hold with respect to the lattice points. So that must mean that I must be able to translate any lattice point from the corner of the unit cell to the center of the unit cell. And then my lattice has to look exactly the same. It has to look indistinguishable from original form. So when I put an atom on a lattice point, which is here on the corner of the unit cell, then that translational symmetry must also hold. So that means I must be able to shift this atom from the corner of the unit cell into the center of the unit cell, and then my structure has to look the same. Of course, this is not the case if in the center of the unit cell, there's a different atom. Okay, like in this case here, the cesium. So for that reason, such a structure is not a body-centered structure, but it's actually a primitive structure. This is an important point to keep in mind. So in this case, we say we have the lattice type P. In addition to cesium chloride, there are many other compounds that crystallize in such a structure. For example, there's an intermetallic phase between copper and zinc that makes that structure. Okay, note that this is not an alloy, okay, but an intermetallic compound. Okay, cesium bromide as well as LiAg. Again, this is an intermetallic compound, not an alloy. Okay. So an alloy, just to remind you that also is a solid solution of one metal in another. Right? That is distinct from an intermetallic compound. All right. So now let's go from the cubic crystal system to the tetragonal crystal system. So what possibilities do we have here? So now in this case, we can either have a primitive cell, or we can have a body-centered cell, an I cell. We cannot have an F-centered cell. Why not? The reason is that if we F-centered, and I do this hypothetically here, so now I center my unit cell so that each face has a center. In this case, however, I can define a smaller unit cell with the same symmetry, which is primitive. Okay? And as long as symmetry doesn't change, I always define the smaller unit cell as my unit cell, not a larger one. Okay? So for that reason, F-centering is not possible. All right, so now what about the orthorhombic crystal system? So in this case, we have 4 possibilities. We can either have the primitive cell, we can have the I-centered cell, we can have the F-centered cell. But in this case, we also have an A-centered cell. So that means that in this case, we do not center all the faces that we have available, but only 2 opposite once. Okay, so now when we have acentering, that means that we center the atom in the BC plane. Okay, so we just define this, for instance, as the lattice parameter B. This would be our lattice parameter C, and that here would define the lattice parameter A. Okay, it's of course arbitrary how you define the lattice parameter. Okay, it's just a question of a definition. So when we have a B-centered unit cell, then we would basically center in the AC planes. When we have a C-centered case, then we would have centering in the AB plane. All right. Then what about the Trigonal crystal system? It's also called the Rhombohedral crystal system. So in this case, only a primitive cell is possible. We cannot center that primitive cell because if we centered it, I would define a smaller unit cell. So previously already said how we can understand the rhombohedral cell. You can actually pull here at the opposite corners of a cube along the space diagonal, and as you do, the symmetry changes from cubic to rhombohedral. Okay, so we still have the hexagonal, the monoclinic, and the triclinic crystal system to consider. For hexagonal, we have only a primitive cell possible. The same for the triclinic case. In the monoclinic case, in addition to the primitive cell, we can also have a C-centered cell. So if you define here this to be the lattice parameter A, and that the lattice parameter B, then basically this is the C plane which is centered. Not only this plane is being centered, also the opposite plane must be centered. All right, so now we got it all, and we can just sum up our results that we have obtained thus far. So we have one lattice associated with triclinic, P. For monoclinic, we have primitive and C centering, so that gives 2. For orthorhombic, we have 4 possibilities to center: primitive, face-centered, body-centered, and A-centered. For tetragonal, we have 2 possibilities: primitive and body-centered. For cubic, we have 3 possibilities: primitive, face-centered, eye-centered. And for trigonal and hexagonal, we only have primitive cells. So now that gives 1 plus 2 plus 4 plus 2 plus 3 plus 1 plus 1 is overall 14. So these are the 14 Bravais lattices in 3 dimensions. So any extended solid which is crystalline crystallizes in one of these 14 Bravais lattices. Therefore, solid state chemists, we have to be familiar with them and we have to understand them. Okay, so I also wanted to briefly review unit cell contents. This is something that you probably all have heard about, but because it's so well important, I briefly wanted to review how you can actually determine how many atoms are in a particular unit cell. So it's a little less obvious then it sounds because unit cells share atoms if the atom is not inside of the unit cell, depending where the atom sits, whether it sits on a corner or a face or an edge, it counts only a particular fraction of a full atom. So let us briefly review this. So generally, when an atom sits on the corner, then because a corner is being shared by 8 cells, each atom only counts for 1/8. When the atom sits on a face center, then a face center is being shared by 2 cells, therefore each atom only counts for 1/2. When the atom sits in the body center, then the atom sits inside of the unit cell, and inside of the unit cell, there's no sharing taking place. Therefore, any atom inside of the unit cell counts fully. So if the atom is located on the edge of a unit cell, then the edge is being shared by 4 other cells, and therefore each atom only counts 1/4. So let us briefly apply these rules to one example, such as the sodium chloride crystal structure. You see here the unit cell of the sodium chloride. You see that one atom type is on the corners. We can define this, for instance, as the sodium. We could also define that as the chlorine. It would give the same results because of commutation, and I will explain later on what that is. So let's define these blue ones here as the sodiums. You see that the sodiums are sitting on the corners, but you see additional sodiums in the face centers here, 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 and here. So there are no other sodiums. So how many sodiums do we have overall? Well, we have these 8 sodiums, which sits on the corner, and each sodium counts by 1/2. So 8 times 1/8, counts for 1/8, not 1/2. So we have 8 times 1/8, and that is equal to 1. So we also have the sodiums at the face centers. So we have 6 face centers, and each atom on a face center counts 1/2. So 6 times 1/2 is equal to 3. So overall, we have 4 sodiums within the unit cell. So what about chlorine? So you see the chlorine atoms, they sit here on the edge centers. There are 4 here. There are 4 more here. And there are 4 more here. So in addition to that, you have this chlorine in the body center of the unit cell. All right, so now how many chlorines do we have? Well, those at the edges, they count 1/4. So we have 12 of them that count for 1/4, and 12 times 1/4, that gives overall 3. So this one here, which sits at the body center, fully counts, and therefore has the counts for 1, and 3 plus 1 is equal to 4. So overall, we have 4 sodiums and 4 chlorines. The number of sodiums and chlorines obviously have to be the same, because otherwise we could not arrive at the stoichiometry of Na1Cl1. All right. So now I could also ask you, well, what is the centeredness of this unit cell? Is it body-centered? Is it face-centered? Or is it primitive? These are the 3 possibilities for the unit cell. Can one of you raise a hand if you know the answer. So nobody seems to know the answer. Oh, we have a raised hand. Okay, can you please speak? Unmute yourself.
It's FCC.
FCC. Yes, that is correct. And why is it FCC? That is because when we have FCC, then translational symmetry with regard to FCC must hold. So that means that any point which is on the corner, which defines the lattice point, must be shiftable to the center of the face. Okay, so that's of course only possible if the atom which is at the center of the face is the same as the atom at the corner. Okay, therefore with face-centeredness, okay, we also have an atom here in the body center. Okay, but you see that this atom is different from the atoms that sit here on the corners. Therefore, translational symmetry from the corner to the body center does not hold. Okay, therefore we have no body centeredness. Of course, we cannot have face-centeredness and body-centeredness at the same time. It can only be one of the two. In this case, it's face-centeredness. Okay, so last but not least, I would like to review what is called fractional coordinates. So fractional coordinates describe nicely where atoms are sitting within the unit cell. Therefore, they're very handy to describe unit cells in general and the unit cell contents. So what is meant by fractional coordinate? Well, we describe here the fraction of the four lattice constant in one particular direction. Okay, that can be in 3 dimensions, lattice parameters A, B, and C. Okay, so for instance, in the case of this face-centered cubic unit cell, where are the fractional coordinates of the metal atoms here? Well, if you define this B, this C, and A perpendicular to that, and if we define this the origin, then this atom here would sit at the position 0, 0, 0. Okay, so there will be 7 other atoms that are sitting on the corner, on the other 7 corners. So they of course all have coordinates, but we do not express these coordinates because they can be expressed by a full translation along one or more lattice parameters A, B, and C. Okay, so for instance, this atom here, this one, would sit on the coordinates 1, 1, 1. Okay, but that's a full lattice parameter A, B, and C, and therefore it's considered a duplication, and so therefore the coordinate is not mentioned further. So now, what about an atom sitting on a face center? So, for instance, this atom here would be described by the lattice fractional coordinates 0, a half, a half. Why is that? Because we need to go 0 in A direction, a half of the lattice parameter B, and a half of the lattice parameter C. Okay? So there are now 3 other atoms that sit on the face centers which are explicitly described. Namely, the one that sits on the fractional coordinate a half, 0, and a half, 0, a half. Okay. Now overall, we have, of course, 6 atoms sitting on the face centers. Why don't we mention the other 3? Again, that is because we can express them by translation along a 4 letters parameter, either A, B, or C. Okay? So that would be, in explicit terms, the atoms that sit on the coordinates 1, a half, a half, a half, a half, 1, and a half, 1, a half. Okay? With these 3 additional coordinates, we would identify the positions of all 6 atoms that sit on the face centers. But we mention only 3 of them because the other ones are produced by translational symmetry. All right, maybe one last example, just to finish up this chapter. We have here the cesium chloride with a primitive cell. So we can say that, well, if you define A this direction, C this direction, and B that direction here, and we define this, the origin of our coordinate system, that then this cesium atom here sits on the position 0, 0, 0. Okay? The 7 other cesium atoms, they are produced by translational symmetry. We do not write their coordinates explicitly. So the chloride, it sits in the body center. So we can describe the fractional coordinate by a half, a half, a half, because we have to go half into A direction, half into B direction, and half into C direction in order to arrive at the center of the unit cell. All right, then that closes that subchapter, and in the next class we will then begin with glide planes and screw axis. And I wish you all a good weekend, and if you have any question, you can ask them now. I'm just stopping the recording at this point.